In this video, I want to review some sections of Chapter 11, Section 3, 4, and 5. In case you were gone for an absence being sick or gone for jazz, I want to run through a few things just to help you get caught up if you need to. I want to start out with Section 11.3, which is rational square roots. The assignment that I gave on this page on 519 is 3 through 48 multiples of 3. There's not a lot of examples, so I just want to run through a couple of the ones that might confuse you. For example 1, you've got the square root of 225. Now on here, always use the calculator first. Give 225 a shot and just see if it has an actual whole number square root. You don't want any decimals as answers on these. And on this one, if you do 225 and hit the square root button, you will get 15. Now the book shows you an alternate example that if you break 225 down into perfect squares, then you get that you have the square root of 9 times 25 underneath the radical sign. Now the 225, this is called your radicand, and this is your radical sign, or just call it square root symbol, that's fine too. Now what you can do under here is take square roots of these independently. So let me give myself a little more space in front of the equal sign. If I have 9 times 25, here's essentially how that 15 over here that we got as an answer comes to be. The square root of 9 is 3, and the square root of 25 is 5. When you bring both of those out, you're multiplying those together, and of course 5 times 3 is 15. So you end up with that same answer. So you're going to be working with that, but sometimes you'll have something left underneath the radical symbol. In this particular section, you don't. If you look at example 3, and this is on page 518, you've got on A the square root of 36, and it looks like a fraction, so 36 over 121. Now if it helps you understand how this works, this is exactly the same as if you split this out into two separate square root operations. The square root of 36 over the square root of 121. And both of these have whole number roots being rationals. So the square root of 36 will give you 6. The square root of 121 gives you 11, and you're at your final answer. Don't go any further than that. The other thing that this section covers is if you have a negative sign in front of the radical sign, you'll want the negative sign in front of your answer. If you have a plus minus sign in front, you'll want a plus minus sign in front of your answer. If there's nothing there, just leave it as nothing, and that's called the principal square root. So if I take the square root of 100, which you know is 10, just leave that at 10. But if it were negative, then you put a negative sign right there. Let's see. On your actual work that you're doing, there are two samples I want to cover with you real quick too. So let me get rid of all this. On sample 1, you're working with the square root of 18 over 32. Alright, now what you can do on this is you can break this down, you can simplify this just as a regular fraction. So since 18 and 32 are both evens, you know they can be reduced by 2. So you can go ahead and reduce that down to 9 over 16. And then take that on to the square root of 9, which is 3, and the square root of 16, which is 4. And you're at your answer. Remember, you're no longer under the square root sign. You've actually pulled it out when you did that operation. So don't put square root signs in your answer. Now sample 2, that one is dealing with the decimal. I really don't have a preference here on the test. You'll be able to use a calculator. So if you put 0.64 and hit the square root sign, you're going to get your answer. But the book does show this as converting it to a fraction of 64 hundredths, which is 64 over 100. Then when you take your square roots of those, the square root of 64 is 8. The square root of 100 is 10. And then reduce that down to 4/5. And you're at your final answer. So that'll get you most of the way through 11.3. I don't think you'll have too many spots where you're going to get stuck. Just don't forget to use your calculator on that. And don't forget to simplify your fractions to try to turn those into perfect squares. Let's move on to 11.4. And this starts on page 521. I signed 1 through 20 on here. Um, what you're looking for on 11.4 is you want to try to pull out perfect squares. Perfect squares are going to be 1 times 1, which is 1, 2 times 2 is 4, 3 times 3, 9, 4 times 4, 16. You're wanting to pull out those perfect squares. So for example 1 on A, you're given the square root of 324. Now, if you use your calculator, you're going to get 18 right away. So that's your first course when you see a number you don't have a square root in mind. So we'll just go around past that. Next one, square root of 75. If you use your calculator to find the square root of 75, you're not going to get a whole number. So what you want to do is try to pull out a perfect square, 4, 9, 16, 25. And 25 works in this case. Since 75 is 25 times 3, the way I show that is once you split that out in the radicand, then take the square root of the one that you can and move that number out in front of your radical symbol. And then simply rewrite what you have left, which is 5 times the square root of 3 to finish up. On C, it's... oh, that was ugly. Let me get rid of that. Alright, on C, you've got a 2 in front, and then you have the square root of 112. Now, sometimes it's not so obvious what you can pull out. But on this one, 4 will go into 112, and I will sometimes show that instead of rewriting it the way we did here, I'll show that as a mini factor tree. I know 4 will come out of it because 4 goes into 100 and it goes into 12. So that is 4 times, let's see, what would that be? 28. Then you can also take another 4 out. And the reason I'm taking 4 out is because that's a perfect square. So I have a 4 here and a 4 here. Well, the square root of 4 is 2. And that's going to multiply by the 2 that was already there. And the square root of that 4 is also 2. So that's going to multiply those by those other 2. I still have a 7 left underneath my radical sign. So my answer is going to be 2 times 2 times 2, which is 8. And then the square root of 7 will remain. And that's what your answers look like for a rational square root, similar to B. And on D, this one is the square root of 891. And it's the same thing. You don't know that one off the top of your head probably, and the calculator is not going to give you a good answer. What you do know is a few divisibility rules. If you add up these digits, you get a multiple of 9, so you can pull 9 out, and 9 is a perfect square. So there are 100 9s in 900, so I need 99 9s to get me to 891. Then of course I can pull another 9 out of 99, and it leaves me with 9 times 11. So this is going to be left underneath the radical sign as my radicand. The square root of 9 is 3. The square root of 9, again, is 3. So my answer is going to be 9 times the square root of 11. All right, so it's a little quick intro to example 1. For example 2, I'm actually just going to completely skip that. That says approximate to the nearest 100th. Just use a calculator if you have any like that. I don't think I assigned you any like that. And you don't have any samples, so your challenge is trying to find the perfect square that you're trying to get to. And if you break it down using a factor tree method like this, it doesn't really matter which numbers you pick, but you are going to take the perfect squares of all the numbers. Let's see. Section 11.5, square roots of variable expressions. Now in this, I'm going to break away from the book for just a second here and just show something quickly. What you're doing now, instead of having numbers under there, you're going to have letters under there too. The square root of y to the second power will be y, because y times y is y to the second. Now if you think about that, the square root of 25 equals 5 times 5. So 5 to the second power equals 25. I should have kept this completely off of there. I might have confused my explanation here. Let me take that away. Alright, so the y square root of y squared is y. The square root of 25, which is the same as a square root of 5 squared, equals 5. What you're looking at is this squared should equal the radicand if you do this to the second power. So in this case, there's only one thing that you need to know. We rewrite this up there. These two cancel, but you need absolute value signs around the y, and here's why that is. We get rid of this part of my explanation. You want to make sure that you don't have any signs that are getting backwards on you. If I put a -1 in for y, here's what would happen in this scenario if I didn't give a limitation of my absolute values. I would be saying that square root of -1 squared would be -1. Now that's actually not true. If I arrow down, I'm not working left to right, I'm working top down. This would be the square root of -1 times -1, which is 1. And the square root of 1 is 1, not -1. Over here, though, you have a -1 writing it down each step. So what you've stated is that 1 equals -1, and that's not true. The way you prevent that from happening is putting absolute value signs around that situation. Now, in contrast, since that was an exponent of an odd power, this would be an exponent of 1. In contrast, let me do the square root of y to the 4th power. That would be y squared. Anytime you have even exponents, there's no way of creating an odd answer. If y is -1, then this would be even, and this would have to be even as well. So you don't need the absolute value limitators on anything with an even exponent. All right? So even and positive. And that'll take away some of the opportunity to have something wrong on a placement test. All right? For examples, example 1, you've got, let's do B. And this is on page 525. For B, you've got the square root of 36x to the 8th. So the square root of 36 is 6, and the square root of x to the 8th is going to be x to the 4th, because x to the 4th squared is what gives you x to the 8th. All right, so that's your answer right there. On C, on here, what you're doing is you're factoring underneath. M squared minus 6m plus 9 is a perfect square. So you have m minus 3 squared. Essentially, these cancel. But since you only have one of these, m minus 3 needs to be put into absolute value symbols. And D, the square root of 18a cubed. Well, you can't take the square root of a cubed. What you're going to have to do is take the absolute value of a squared, and you're going to have an a left over as your odd one. Now, 18 is 9 times 2. So here's my recommendation for how to do that. The square root of 9 is 3. The square root of a squared is a, leaving you with 2a underneath your radical sign. So it's 3a, absolute value signs, square root of 2a. Again, here's your 1 in as an exponent, but you don't need to put that there. For example 2, you've got 9x squared equals 64. On this, divide both sides by 9 to solve for x squared. And then to solve for x, what you're going to do is take the square root of both sides. And when you do that, x equals, square root of 64 is 8, the square root of 9 is 3. And you actually have two different roots on those. So always remember to put a plus minus in front of that. Alright, I've only got about 10 seconds left of record time. So hopefully that'll give you a good head start on what you're doing, and then we'll do more questions on Monday. Good luck with it.